In this video, we'll look at optimization with derivatives. The question comes from your textbook, page 215, number 10. I'll read it to you. The fuel cost per hour for running a ship is approximately 1/2 of the cube of the speed plus additional fixed cost of $216 per hour. Find the most economical speed to run the ship for a 500 nautical mile trip. Okay, well, we'll begin by writing down what we just learned from that problem, or we'll piece together what we read from that problem using an equation. So I'll call that equation cost. The cost equals half the cube of the speed, so 1/2 the velocity cubed, plus 216 fixed costs. That's the cost to run the ship per hour, so I need all that times time. But the problem is, if I have two variables, I don't really know how to do that in this class, so I'm going to need a second equation to work with this. And that equation is going to come from the 500 nautical mile trip. We do distance equals rate times time, so 500, the distance, equals velocity, the rate, times time. Let's call this equation 1 and call this equation 2. And from equation 2, I'll get t by itself by dividing by v. And so t equals 500 over v. Let's call that 2a, adjusted equation 2. And we'll sub 2a into equation 1. So the cost now equals 1/2. We're still building this cost equation. 1/2 v cubed plus 216 times t, but we just have t, which is we're subbing in, is 500 over v. Okay, we'll now multiply everything in the brackets times 500 over v. So 500 times 1/2 leaves 250. And v cubed times 1 over v, that's like v cubed divided by v, which gives you v squared. And now I'll put a plus. 216 times 500, that's 108,000. So we get 108,000 over v. And we're going to want to take the derivative, but in our class we need to do the derivative using only product rule and chain rule. We don't have a quotient rule. So we'll bring that v up, and we get 108,000 v to the -1. And now we're going to take the derivative. What's the derivative of c? As we're trying to maximize here, well, we get, what's the derivative of c? We get 250 times 2, which of course is not 250, it's 500 v. And then the derivative of the second part there, the -1 comes down, multiplies by the coefficient, and the exponent subtract 1. So we get that. Why are we doing the derivative? Because we're trying to find the max or min, which occurs at a critical point, which is where c prime would equal 0. So set c prime equal to 0. And now we're going to try and solve. Get 500 v, I'll just rewrite this part here, but over v squared. And the reason I wrote it like that is because now I think you'll see the easiest way to work with this is times everything by v squared. When I do that, 0 times v squared is 0. 500v times v squared is 500v cubed. And these v squareds cancel out, and you're left with -108,000. I'll go up here. I'm going to add 108,000 to both sides. I get 108,000 equals 500 v cubed. And now divide both sides by 500. And you get v cubed is, what's v cubed? 108,000 divided by 500. And you get 216, a nice number, because now we're going to take the cube root of that. We don't have to worry about plus minus because it's a positive number. What's the cube root of 216? I actually know it, but let's do the third root of 216, and you get 6. And the velocity equals 6. We're actually done. You might wonder, why didn't we check the endpoints? Well, if time were 0, velocity is 0, obviously the endpoint of 0 is not going to work. If your velocity is 0, there's no way you're going to maximize your cost. If your velocity is 0, you're going nowhere. And what's the high point of velocity? Obviously the ship has some top speed, but we don't know what it is. And so the top speed for us would be infinity, which obviously, of course, is not going to minimize your costs. And so, therefore, we're done. We've found the optimal speed to minimize costs. Let's write that down. I'll read the question again, what it asked for. Find the most economical speed to run the ship. The most economical speed is 6, and I just have to look at the question to see the units. The units were in nautical miles, whereas 6 nautical miles per hour. And there we've done it. We've done optimization with derivatives. We made 2 equations, isolated for one variable in the second equation and subbed it into the first. Did a little bit of simplifying and then took the derivative and set it to 0, which allowed us to find the best speed, which in this case is 6. And we're done.